For lesson 34, we're back to our PhET demonstration, and let's review what I talked about with the current here and so let's put on some, let's put the battery right there. And nothing's happening here. We're on sodium. We have to shine some pretty heavy UV light. Actually, let's put the battery configuration that way. Ooh, no intensity. That's why it's not happening. So there we go. We have to let's shine some UV light on it. Oh, it even works for visible light for sodium. And what we said was, so we're watching, let's have a look at the current here. Let's increase the current. So that's actually quite a bit of current. And we're going to adjust the intensity. So what we said in the last lesson when we're doing this is as we increase the intensity, you'll notice that the current increases. Why is that? Simply when you increase the intensity, more electrons are coming off the surface. Let's make it really obvious by there we go. So more electrons are coming off the surface, and then if I decrease the intensity, the current is going down. However, the electrons are still moving at that really high rate of speed, so their kinetic energy has not been affected, only the number of electrons, therefore the current, because current is the number of electrons, right? It's current, I equals Q of T, the number of electrons per second. That's what current is. So when I increase the intensity, I increase the current because I'm increasing the number of electrons. However, what is making the electrons go slower and faster? And that is the frequency of the light, right? So now I'm decreasing the frequency here. I'm going to higher wavelengths. So I'm decreasing the frequency, and all of a sudden, no eject. Oh, there's one. Okay, but if I increase it over here, I get electrons moving really fast. So the frequency of the light is related to the energy of the electrons. Yeah, I'll say that again. The frequency of the light is directly proportional to the kinetic energy of these electrons. The intensity has nothing to do with the kinetic energy. It only has to do with the number of electrons that will reach there. Which brings us to, let's pause that, photoelectric effect graphs. And the graph that we're going to be dealing with is the relationship between energy and frequency. And we just said that the energy is directly proportional to the frequency. So if we increase the frequency, we will increase the energy of these emitted electrons. The graph looks like this, however, and the graph, an EF graph, the photoelectric effect, will always have an x-intercept, and that x-intercept represents the threshold frequency. So again, that's the frequency, the lowest frequency that will get electrons off the surface of the metal. And the y-intercept, since the y-intercept occurs on the y-axis, and the y-axis is energy, is going to be the work function. So this is what graphs for various metals look like in the photoelectric effect. And you can see it says the threshold frequency is the x-intercept, so the y-intercept is the work function. And every metal has, now, I gave away the secret by going on to the next page. What is the slope of these lines? The slope of the lines is Planck's constant, because of this right here. E equals hf, and therefore h equals E over f, and E is the rise, it's the y-axis, and f is the run. It's the x-axis, right? Y-axis, x-axis. And therefore, the rise over the run will give you Planck's constant. And you can see for every metal will have a different threshold frequency and a different work function, but they all have the same slope. So for this example here, example number 1, you've got 3 different metals, copper, calcium, and selenium, and they have different work functions, but you'll notice the slope of all of these is the same. Why is it the same? Because the slope is a constant. It's Planck's constant. Okay, and the question is just asking for So this question says, the following graphs show the effects of shining different frequencies of light on 3 different metals. Identify which line represents each metal. Well, what we can do for this is extend the graph and then extend each of these lines. And luckily, they're the colors that I want. And then just match them up to what the numbers could be. So we're dealing with work functions here. Obviously, the lowest one down here, this is going to be the negative 5.11. Right? And then the next one is 4.7 and 2.9 blue. So just based on the work functions, you can match up the metals with the correct work functions there. So calcium is the blue, and copper is the red, and selenium is the green. Okay, and that's it. That is the photoelectric effect graphs. On the lesson 35, which is the Compton effect. Oh, you're gonna love this one.